What if I told you that the universe you're sitting in right now doesn't actually exist in three-dimensional space?
Which is a pretty wild thing to hear right off the bat.
I mean, yeah, it sounds crazy, but imagine there is no fundamental up or down, no empty void, and like no continuous fabric of reality at all.
Right, just this idea that everything underneath atoms and quarks, reality is just a giant tangled web of invisible code.
Exactly. Like it's constantly updating itself, almost like a cosmic software program. Welcome to today's deep dive, by the way, where our mission is to see if the entire cosmos can be built from something shockingly simple.
Yeah, and we are looking at Stephen Wolfram's fascinating writings today, specifically his piece on a potential path to the fundamental theory of physics.
And it's beautiful. I mean, okay, let's unpack this because usually theoretical physics means dense, impenetrable math,
Oh,
right?
completely. Just chalkboards filled with equations that nobody can read.
Yeah, but this approach, it feels like we're looking at the raw source code of reality itself.
Well, if we connect this to the bigger picture, for a century now, physics has been totally stuck.
Right, trying to reconcile the very big with the very small, relativity and quantum mechanics.
Exactly. They speak completely different mathematical languages. And Wolfram's 50-year quest basically says, hey, instead of adding more complex math, we need to go underneath space and time.
To find the discrete, simple rules generating them. Which makes sense because before we can build a universe, we need to know what raw materials we're working with.
Right. And it turns out the universe isn't a box filled with stuff. The box itself is the stuff.
Oh, wow, that's a great way to put it. So, where did this idea even start?
Well, it goes back to Wolfram's realization in the 1980s. He was working with cellular automata, and he saw that simple rules, applied over and over, can create infinitely complex behavior.
So, we don't need insanely complicated equations to get a complex universe.
No, not at all. You just need a tiny rule applied a staggering number of times. But to understand this, you have to look at something called a hypergraph.
Right, the hypergraph. And to visualize this, you really have to strip away any concept of geometry, right?
Completely. At the lowest possible level, the universe is just abstract points or nodes and abstract relations between them.
So, no shapes, just like what is connected to what.
Yes, pure topology. You apply a trivial rule, like whenever a node connects to two others, create a new node.
And when you apply that rule zillions of times across the universe, which has something like 10 to the 400th power of these points, right?
Yeah, an unfathomable number. The graph grows and tangles until a macroscopic structure emerges.
And that structure just looks like a three-dimensional shape to us. It's like, think of a massive social network like LinkedIn or Facebook.
Oh, that's a really good analogy.
Right, because you don't have a physical map of Facebook. It's just who knows who. There's no physical distance.
Just degrees of separation.
Exactly. But if you draw out billions of those connections, a distinct complex shape emerges out of the data. You see dense clusters for big cities.
And, the crucial thing there is that nobody programmed the shape into the social network.
The shape emerges entirely on its own.
Right. And philosophically, that's what's happening to our universe in this model. We aren't putting the shape into the model. Space is an emergent property.
Which means we have to completely throw out our intuitive understanding of space and time.
We really do. Because if space is just this unimaginably massive web, it's not a continuous void. It is discrete. It's chunky.
Chunky space, I love that. The source uses the analogy of water for this, doesn't it?
Yeah, and it's perfect. When you're swimming, water feels like a continuous, smooth fluid.
Right, we even use continuous math like fluid dynamics to describe it.
But if you zoom in far enough, it's just discrete, bouncing water molecules. Space operates the exact same way.
So at our scale, it feels continuous, but underneath it's just this abstract mesh of points.
Exactly. And because it's just a mesh, it doesn't even have to be perfectly three-dimensional.
Wait, really? What do you mean?
Well, depending on how the graph grows, it can form fractional dimensions. Like, it could be a 2.7-dimensional fractal at a certain scale.
That is deeply weird to think about.
It is. But the specific rules governing our universe naturally limit it out to a solid 3D space at our macro level.
Okay, so if space is just the density of this web, how does that explain something like gravity?
So curvature happens when the growth rate of connections inside a specific area of the graph changes.
Oh, like drawing a circle on flat paper versus a sphere.
Exactly. On flat paper, the area grows predictably. On a curved sphere, the area inside grows differently. Gravity is literally just the structural curvature of this network.
Okay, but what about time? Because for a century, physics has told us that space and time are the same thing, the space-time continuum.
Right, but lumping them together might have been a bit of a wrong turn. In this model, they are completely different.
Wait, really? How so?
Space is the structural layout of the hypergraph, but time is the inexorable computational progress of applying those rules.
So time is the actual doing of the computation.
Yes, time is computational. You can't just skip ahead to the future.
Because the universe literally has to do the irreducible computational work to figure out what happens next.
Exactly.
But wait a minute, I have to push back here. If time is just the ticking of a cosmic computer processor, how does that square with Einstein?
You mean relativity?
Yeah. We know time is relative. Two observers moving at different speeds experience time differently.
That is a fantastic point. And to resolve it, we have to look at what happens when the universe tries to apply rules in different orders.
Okay, color me intrigued.
It introduces this concept called causal invariance.
Right, the sorting algorithm analogy from the readings. I love this part.
It really clarifies it. Walk us through it.
So imagine a computer program sorting the letters BA into alphabetical order.
The rule is simple. Swap any letters that are out of order.
Exactly. But you have two instances of BA in that string. Which one do you swap first?
And the beauty of causal invariance is that it doesn't matter.
Right. You can swap the first pair, the second pair, or both at once. The paths branch out, but they always merge back together to give you AAB.
And our universe does the same thing. Paths of history branch out as updates happen in different orders, but they eventually merge back together.
So the underlying network of what caused what the causal graph remains completely identical.
Exactly. And this directly leads to relativity. Observers divide this causal graph into slices of time, which are called foliations.
Right, like a sequence of this happened and this happened.
Yeah. Now, imagine every update in the hypergraph is a computational step. If you're standing still, your local updates just move you forward in time.
But if I'm moving really fast through space,
Then you are forcing the graph to use its computational updates to physically relocate your nodes.
So I'm basically using up my local processing power to move.
Precisely. Computation is finite. So if you're using it to move through space, there are fewer updates available to progress your internal clock.
So my time literally slows down compared to someone standing still.
Yes. You construct a different slice of time, but because of causal invariance, the underlying rules stay identical. This perfectly derives special relativity.
Here's where it gets really interesting, though, because this also redefines what energy and mass are, right?
Oh, absolutely. In this framework, energy is simply the flux of causal edges through space-like surfaces.
Just the amount of causal information propagating through time.
Right, and mass is the flux of causal edges through time-like surfaces.
And the ratio between them relies on the maximum speed of information transfer in the graph, which is the speed of light.
Which elegantly gives us E equals mc squared.
That's insane. E equals mc squared isn't just a math trick here. It's a structural reality of how the universe communicates information.
And it goes even further. This model actually reproduces Einstein's vacuum equations.
Wait, so the curvature of space interacting with the energy and mass flux?
That is gravity.
Wow. We just derived 100 years of astrophysics from a web of connected dots. But what happens when we zoom way in?
To the subatomic level.
Yeah, to the incredibly tiny, probabilistically weird world of quantum mechanics.
Well, if the universe has causal invariance, it doesn't just pick one path. It does all possible rule updates at once.
So it's constantly creating branching paths of history.
Yes, and this creates what Wolfram calls a multi-way system.
Okay, and if we take a slice across all those branching paths, we get something called branchial space, right?
Exactly. Branchial space is an abstract space where quantum states are mapped by how entangled they are.
So instead of mapping physical distance, it maps entanglement distance.
Right. And here's the mind-blowing unification. General relativity and quantum mechanics are the exact same idea.
The exact same idea, just operating in different spaces.
Yes. Einstein's equations in physical space describe gravity. Feynman's path integral in branchial space describes quantum mechanics.
That is just beautiful. But I have to ask, if the universe is taking all these branching paths at once, why do you and I experience a single definite reality?
Right. Why isn't your coffee cup in a superposition?
Exactly. Why is it just sitting there on the table?
It comes down to the quantum observation frame. You, the observer, are also part of this branching multi-way system.
Okay.
But to process information, when you make a measurement, you are essentially bundling those branching paths together.
So I am forcing a foliation that freezes time in the multi-way graph.
Exactly. You are creating a sort of reality distortion field that isolates a classical outcome. The universe keeps branching, but your perception is locked into a shared history.
Observation isn't magic, it's just a structural freezing of the graph. That makes so much sense.
It really demystifies quantum mechanics.
Well, let's stress test this unified theory. Let's throw it into the most extreme phenomena in the cosmos. Black holes.
Okay, let's do it.
In traditional physics, a black hole is just incredibly dense gravity. What is it in a hypergraph?
It's an actual literal disconnection in the causal graph.
Wait, like a piece of the universe just breaks off?
Pretty much. The hypergraph gets so incredibly dense that a localized section pinches off. Causal edges can go in, but they can't point out.
So information is just trapped. Does this happen in branchial space too?
Yes, as an entanglement horizon. Quantum information gets completely frozen at the surface.
Because there's a maximum entanglement speed, right?
Yes, called zeta. And it's estimated at 10 to the power of 102 states per second.
Okay, visceral question for you. If I cross the event horizon in physical space, standard physics says I get spaghettified by gravity.
Stretched into a string of atoms, yeah.
What happens to me in branchial space?
This raises an important question about consciousness in this model, because you get elongated in branchial space too.
I get quantum spaghettified.
Basically, yes.
Yeah.
You become so distorted across the multi-way graph that your nodes can't entangle fast enough to keep up with the updates.
Oh my God.
You literally lose the physical mechanism required to form a classical thought or make a quantum measurement.
So my perception of a single reality just completely dissolves. That is terrifying.
Terrifying, but structurally elegant.
Okay, let's pivot to dark matter. Galaxies spin faster than they should, implying invisible gravity. How does the hypergraph explain that?
Well, mention the elementary lengths first. The scale of a single connection in the graph is roughly 10 to the negative 93 meters.
Which is unfathomably small. And in this framework, an electron is just a stable local lump of space, right?
A tangled knot in the hypergraph, yes. And Wolfram's model predicts something called oligons.
Oligons, what are those?
They are tiny, incredibly light particles with very few hypergraph elements. They are incredibly simple knots.
So simple they don't interact with regular matter or emit light.
Exactly. But they still have causal edges, which means they still have mass.
Oh, I see where this is going.
Right. If the early universe left behind trillions of these oligons, they would pool in galaxies.
And their collective mass would perfectly explain dark matter.
Exactly. No need for exotic, magical particles, just simpler knots in the graph.
It's incredible. We've built space, time, relativity, quantum mechanics, black holes, and dark matter, all from simple rules.
We have.
But that brings up the ultimate philosophical question. Out of all the infinite possible rules, why does our universe run on this specific one?
That is the big one.
Yeah.
And the shocking answer is, it doesn't.
Right, what?
The universe isn't running just one rule. It is running all conceivable rules simultaneously.
All of them, at once.
Yes. This is what Wolfram calls ruleal space.
Okay, so what does this all mean for the multiverse? Are other universes not physically out there, but like right here?
Yes. They are overlapping us right now. The universe is just a universal computer running every possible code.
Running on an operating system we just can't perceive.
Exactly. Any rule capable of universal computation is happening. The only reason our universe looks the way it does is because of our description language.
Or description language.
The way our biological and technological senses choose to decode the data. We are just tuned into a specific reference frame in real space.
Wow. So it's like a cosmic television, and we're just locked onto one channel, but all the other channels are broadcasting in the same room.
Exactly. The only thing truly special about our universe is us and how we observe it.
That is a staggering paradigm shift. I mean, to summarize this incredible journey for you listening, we started with abstract dots and lines.
And watch continuous space emerge from it.
We realized time is just a computational ticking clock. We united Einstein and quantum mechanics into the exact same mechanism.
And discovered that reality is just one channel on an infinite cosmic TV.
Escaping the information overload of purely mathematical physics to find such a simple foundation is just profoundly beautiful.
It really is. It changes how you see everything.
And before we go, there is one final awe-inspiring concept to leave you with.
Oh, about the early universe.
Yeah. Because the early universe expanded incredibly fast from perhaps a single tiny loop of these nodes, it's conceivable that the original chunky discrete structure didn't get entirely erased.
Which means it might still be out there.
Exactly. So next time you look up at the night sky, remember that the foundational rule of our universe might literally be painted across the stars in the cosmic microwave background, just waiting for us to decode it.